Welcome back to Crystal Classroom. Today we'll be discussing how to actually screen a compound. I will emphasize that every compound is different, even if some of them show similarities, so there isn't necessarily a one-size-fits-all strategy, but we will cover the basics. The first facet is solvent exposure. A compound may crystallize in different forms depending upon the solvent available. This is one of the most common factors and one that needs to be explored broadly. Many times, pharmaceutical syntheses will have a recrystallization step at the end, and whichever solvents are present there should be examined to at least identify the potential for phase impurities at that stage. This will also help identify solvents prone to forming solvates, which we may want to avoid. More on that in the next video. The next aspect is temperature. Evaluating the outcomes at both elevated and reduced temperatures is important. Some phases may convert at different temperatures, such as a hydrate surrendering its integrated water content at elevated temperatures, or a metastable phase converting to a more stable phase at lower temperatures. Solvent and temperature can be combined to evaluate if a solvated phase might be avoided by simply increasing the temperature, or if an anhydrous phase might solvate at a lower temperature. Third, there's a question of kinetics. A phase that crystallizes slowly out of a mixture of ethanol and heptane might not be the one that forms if heptane is rapidly added to a saturated ethanol solution. Consider yourself as the chemist performing a lengthy and complicated synthesis, followed by an isolation in ethanol and heptane. For this example, we want to limit it to two options. You can add heptane directly to an ethanol solution to precipitate it, or heat the ethanol solution, then mix heptane in and cool it slowly across 6 hours to crystallize it. I would prefer the faster option, but what if that generates a phase with terrible water solubility compared to the slow cooling process? The last thing I want to mention in this portion is the word metastable. A metastable phase is one that is not the most stable in a specific set of conditions. A phase which is stable at one set of conditions might be metastable at another set of conditions. We briefly touched upon this in our earlier video about monotropic and enantiotropic relationships. The part that I want to mention here is that labeling a phase as metastable can only be done after another phase is observed. If a phase believed to be stable spontaneously converts into a different phase, then the stable phase was actually metastable, and the phase is essentially demoted. This is one of the more insidious issues when it comes to polymorphism and identifying the landscape. As such, there are also experiments that cycle conditions repeatedly to give numerous opportunities for a more stable phase to appear. Once a more stable phase does appear, it will act as a seed, and the conversion into that phase is inevitable.